Welcome back. We've been talking about rates of convergence of the subgradient method and also gradient descent, and the results that we've gotten so far depend on properties of the function. So let's just briefly review what we've seen so far. So our subgradient method, remember that this is not a descent algorithm, so have to resist the temptation of calling it subgradient descent. The algorithm updates xt to xt plus 1 equal to xt minus our step size times gt, where gt is an element of the subdifferential of f at xt. And gradient descent is essentially doing the same thing, except the subdifferential for a differentiable function contains just one element, which is equal to the gradient. Now we saw that as long as our function is convex and Lipschitz, so remember what Lipschitz means in the context of speaking about the function f, which we're minimizing, is that its subgradients are uniformly bounded. So to remind you, what this means is that there exists some constant, capital G we'll call it, so that the norm of G is bounded above by capital G, and this holds for every G in the subdifferential. So as long as our function f is convex and satisfies this property, then we saw that the subgradient method guarantees that after t iterations, our error, in other words, our suboptimality, is some function, is bounded above by some function of 1 over square root number of t, where t is the number of iterations. Another way to say this is that in order to obtain error epsilon, we need 1 over t squared iterations. Again, error means suboptimality. Oops. 1 over epsilon squared iterations. Gradient descent for smooth functions was better, and remember why. We had the self-tuning property. That means that we could take a step size that was fixed and unrelated to the number of iterations we wanted, number of error, final error target that we had. So here we saw that the error after t iterations scaled like 1 over t, which again is equivalent to, for error epsilon, we need order 1 over epsilon iterations. Quite a bit faster. And if we have smoothness and strong convexity, then we're even faster. We saw that our error scales like kappa minus 1 divided by kappa plus 1 raised to the t. Sorry. After t iterations, which basically is equivalent to, for error epsilon, as far as my scaling here, we need something like kappa times log 1 over epsilon. So you see the dependence on epsilon is much faster. And kappa here is the condition number, which is, if beta is my smoothness parameter and alpha is my strong convexity parameter, then beta over alpha is kappa. So we can see that what means more smooth? So a function is more smooth if I can bound it above with a quadratic that opens up more slowly. That would mean a smaller beta is required. Remember, beta is this coefficient of how quickly my quadratic that upper bounds the function how fast that opens up in the case of for smoothness. So for a function that is very, very smooth, I can take beta small. On the other hand, what is alpha? Alpha is the strong convexity parameter, which tells me how quickly my quadratic lower bound is able to open up. We want more curvature. Remember, the reason that we needed strong convexity was so that we could guarantee that when we're far away, our gradients are very big, and so we make a lot of progress. So we would like to lower bound with a big quadratic, and we'd like to upper bound with a slower, more slowly opening quadratic. But really, actually, what matters, and this bound shows that this is really crucial, is that ideally we'd like those quadratics to be as close as possible. We don't want a very big gap. In other words, we don't want our function to be opening up extremely quickly in some directions, and yet in other directions to be very, 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 very flat. Because that would mean that alpha is very small, beta is very big, and this value kappa, beta over alpha, would be very large. And you can see on either side of the bounds here, so on the left-hand side, when kappa is very, very large, this fraction here approaches 1. And 1 to the t, it does not shrink as quickly as a smaller number to the t. As kappa shrinks, now how small can kappa be? Kappa is always greater than 1. So as kappa shrinks to 1, you can see that this constant here, kappa minus 1 over kappa plus 1, shrinks to 0. And something small raised to the t, of course, is going to go to 0 quite quickly. And we see this on the other expression for the error. The larger kappa is, we see the dependence on the number of iterations. So a natural question, now that we've derived this, is are these optimal? So is it possible, for example, that our analysis was loose, or is it possible that there is a better algorithm out there? So this is by itself a subtle question to ask, because there's no such thing as an optimal algorithm for a specific optimization problem, because every specific optimization problem has an answer. So the algorithm that just outputs that answer is unbeatable for that specific function, but of course is not going to be very good for other functions. So this is how we're going to make this concept a little bit more precise, and this will allow us to reason about optimality of certain algorithms. So really the question is, we're trying to solve the problem, minimize f of x. And for now, let's just say that our constraint set is everything. We're trying to solve this problem. Now, the way to make precise this idea of complexity and optimality in terms of convergence rate is to say, what do we know about our function? What do we use? And for every single algorithm that we've seen so far, we've found that all we need is to be able to evaluate the function and also evaluate its gradient, or to get an arbitrary element of the subdifferential. So in other words, we can think about this as though we don't actually know our function f at all. All we have access to is something that I'll call an oracle. And whenever I feed it x, it returns a valuation of the function and either the gradient of f at x if my function is differentiable, or it returns some element of the subdifferential if my function is not differentiable. So if you think back to gradient descent and subgradient descent, so the subgradient method, we can run either one of these without knowing anything about our function f, as long as we just know, as long as we have access to this oracle. Okay, so this gives us a way to make a little bit more precise what we mean by optimality and complexity. So the question now becomes, let's consider only algorithms that can be cast as having access to our function only through this oracle. So suppose the only access we have to our function f is through the oracle. Then we can frame the question as follows. How many calls to the oracle do we need? In the worst case. Over a class of functions. In order to guarantee error epsilon, suboptimality epsilon. So what's interesting about this, the way we've framed this question, is that we're making no assumptions about what you do once you get back the gradient or the subgradient of f. You could be doing some incredibly complicated procedure, possibly exponential time. It doesn't matter. This question doesn't care about that. It's just saying, how many times do you need to evaluate this oracle? So here are some results on that. So the oracle, and these are called oracle-based lower bounds, and they say that for the class of Lipschitz convex functions. Okay, so this is the class for which subgradient method guarantees 1 over square root of t error after t steps. There is no algorithm which can guarantee error better than 1 over square root of t for all functions in this class. In other words, in the worst case. So let's compare this to what we had. This is actually great news. This tells us that the subgradient method is, in this sense, unimprovable. Again, it's important to just dwell a little bit on what the consequence of this is. When we say that it's unimprovable, that doesn't mean that if I have a particular function that's Lipschitz and convex, I can't find a better algorithm than subgradient descent. That doesn't mean that at all. It means that I can't find an algorithm that uses fewer than t squared evaluations. I mean, 1 over epsilon squared evaluations to get epsilon error, and is able to promise that for every single function in this class. So in other words, if you know something special about your function, if you know something else about its structure, and we're going to see that in other lectures, that if we know something more about our function, we can in fact do better. If you don't have any other information about your function, then this is the best that you can do. So in this sense, the subgradient method is optimal. The news is not as good for the case of smooth functions. So for smooth functions, I'm not going to repeat all of this writing and discussion. I'll just say that the lower bound is order 1 divided by t squared, which corresponds to 1 over square root of epsilon. And we should compare this to 1 over t, which is the convergence rate we had for smooth functions, which corresponds to 1 over epsilon. So again, this is a lower bound. This is not saying that here is an algorithm that does better than your gradient descent algorithm. It's actually just saying that there is no algorithm that can do better than 1 over t squared. So of course this leaves open the question, can we do something better? And for smooth and strongly convex functions, with parameters beta and alpha, so let me write that, for beta smooth and alpha strongly convex functions, the lower bound is square root of kappa minus 1 over square root of kappa plus 1 raised to the t. So we should compare this to what we had, our result for gradient descent, which was kappa minus 1 over square root of kappa plus 1. Now, remember that kappa is equal to beta over alpha, and in particular, that means it's greater than 1. And that means that square root of kappa is less than kappa. And as we discussed, this bound is better when kappa is smaller. And therefore, when we replace kappa by square root of kappa, we get a lot. We get something faster. So the pressing question for us is, looking at these two, can these be improved? Can we find an algorithm to match these? Whenever you derive lower bounds, you don't a priori know that the answer is yes to that question. But it's suggestive. And it also tells us that we don't need to try for the case of subgradient because it's not possible in the sense that we described above. So it's worth having a little bit more discussion before we close this section on the oracle model, and in order to understand exactly what this means. So the basic assumption here is that we have this oracle, and this is the only thing we know about our function. Is that reasonable? I mean, is that ever the case? Do you ever really want to minimize something where you don't know anything else about your algorithm? I'd say that it's very rare that this is in fact the model that we have. So in that sense, how is this helpful to us? Well, it says the following thing. One way to think about this oracle model and what the takeaway is, or what it guarantees, is if we develop any algorithm that only uses evaluations and of the function and the gradient, then we can imagine that we have only access to the oracle. In other words, even if you know f, if the algorithm that you develop only uses evaluations of f and evaluations of the gradient, then even if you didn't know f and you only had access to the oracle, you would be running exactly the same algorithm, and therefore that means that you're bound by whatever lower bounds we have from the oracle model. So in other words, again, if we develop any algorithm only using evaluations of f of x and the gradient of x, then we are bound by what we've called these oracle lower bounds. So, just as an example, maybe it would be somehow useful to keep track of our entire history of our trajectory and all of the gradients, and then somehow have some complicated function that produces the next xt plus 1. So that's possible, and possibly this function, we could keep asking ourselves, what if this function is arbitrarily complex? Could we do better? Could we keep doing better and better and better? And the oracle bound exactly tells us how well could we expect any algorithm to do, because no matter what your algorithm is that's taking the history and producing xt plus 2, again, all it's doing is using evaluations of the function, evaluations of the gradient, and so you're bound by the lower bound. motivated by this gap between the lower bound and the bounds that we had for gradient descent, we're going to next look at how we can potentially improve and try to close that gap. We'll pick that up next time.